Welcome back everyone. We can solve some gate and net questions based on the topic number system. The first question is consider the equation 123 to the base 5 is equal to xa to the base y with x and y are unknown. The number of possible solution is, that means we need to find the number of possible solution for this x and y. Y is actually the base here. And for solving this, we need to consider this pattern in base 2 system. Two different symbols we can use, they are 0 and 1. In base 3 system, we can use three different symbols or digit like 0, 1, 2. In base 4, we can use four different symbols and the symbols are 0, 1, 2, 3. Right? So on in base 8 system, we can use 8 different symbols and the symbols are 0 up to 7. And in 9, we can use 9 different symbols for representing different numbers of base 9 system and the numbers are ranging from 0 to 8 and so on. Similarly, we can consider any base system. Okay, and for solving this, we need to consider this in the decimal form. How to convert this into its decimal form? First consider this. To get its decimal equivalent, we need to multiply different positional value with its corresponding digit. That is 5 to the power 0 into 3 plus 5 to the power 1 into 2 plus 5 square into 1. So by solving this, we get 38 in decimal. Similarly, we can represent this in the decimal form, that is y to the power 0. Y is the base, so y to the power 0 into 8 plus y to the power 1 into x, like this. That is x into y, that is xy plus 8 into 1, 8 in decimal. So based on this equation, we can equate these two values. Xy plus 8 is equal to 38. By rearranging, we get x and y equal to 30. So the product of this x and y value is obtained as 30. Now we need to identify different possible values for x and y so that its product is equal to 30. So the one possibility is this. X into y equal to 30 means we can take x with value 1 and y equal to 30, or in other way x equal to 30 or y equal to 1. And next possibility is x equal to 2, y equal to 15, or x equal to 15, y equal to 2. Next option, x equal to 3, y equal to 10, x equal to 10 or y equal to 3. One more possibility is there for the x and y value, x equal to 5, y equal to 6, x equal to 6, y equal to 5. Okay, so these are the these are the 8 different possibilities for x and y equal x into y equal to 30. So now consider in this base y system, one of the symbol is 8. So, while analyzing this pattern, it is clear that beyond this, that is in base 9 system and beyond that, we have the symbol 8. Below this 9, that is in base 8 system, base 7 and all, here we haven't the symbol 8. Right? So, the possibility for the base value is greater than or equal to this 9. Why? Because the symbol 8 is present in this representation. This 8 is present only above this base system. That is base 9, base 10 and base 11 and all. In all these base system, that is the base value greater than or equal to 9, the symbol 8 is present. Based on that, we can conclude that our y value must be greater than or equal to this 9, right? So based on that, in this case, here y is equal to 30, that is greater than 9. But here y equal to 1, which is not greater than 9. So this particular combination, that is x equal to 1 and y equal to 30, which is a possible solution in this case. But this is not, because here y equal to 1. In base 1 system, the symbol 8 is not present. We can't use 8 in base 1 system. That is why this particular combination is not possible here for this x and y. And in this case, here again y equal to 15, 15 is greater than 9. So this particular combination x with 2 and y equal to 15 is again a valid combination for x and y here. But here the second combination is not valid here because y equal to 2, which is less than 9. In base 2 system, the symbol 8 is not present. So this is not a valid combination here. And again here y equal to 10, 10 is greater than 9. So this is again a valid combination, x equal to 3, y equal to 10. And here y is 3, 3 is less than 9. In base 3 system, the symbol 8 is not present. So this particular combination is not valid here, but this one is valid. And in these two combinations, here y is 6, here y is 5. These two are less than 9. Here the symbol 8 is not present. Right? So how many possible solutions are here? 3 different x and y combinations. So option C is the right answer. Next question is the smallest integer that can be represented by an 8-bit number in its 2's complement form. The smallest number that can be represented using 8-bit in 2's complement form. For solving this, we need a basic information, that is the range of numbers that can be represented in 2's complement form is this: minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. This n is actually indicating the number of bits used for representing binary number in 2's complement form. Here it is given that the number of bits used here is 8. So while applying n equal to 8 here, we get this minus of 2 to the power 8 minus 1 to plus 2 to the power 8 minus 1 all minus 1. That is minus of 2 to the power minus 7 to plus 2 to the power minus 7 minus 1. That is minus 128 to plus 127. In this range, which is the smallest number? This minus 128 is the smallest number. So option B is the right answer. That is the smallest number that can be represented in 2's complement form using 8-bit. So option B is the right answer. Next is the number of ones in the binary representation of 3 into 4906 plus 15 into 256 plus 5 into 16 plus 3 are number of ones present in the binary representation of this. After evaluating this, we need to convert that value into its binary, and we need to calculate or count the number of ones present in that. Okay, and we need to get the number of ones present in the binary representation of this. And the options are like this: 8, 9, 10 and 12. So we can solve this in a simple way, that is, we can represent this 3 as 2 plus 1. And this 2 is represented with or 2 is represented as a power of 2, like 2 to the power 1, and 1 can be represented as 2 to the power 0. Next is 4096. This can be represented as 2 to the power 12. Right? Then 15 can be represented as 8 plus 4 plus 2 plus 1, which is 2 to the power 3 plus 2 square plus 2 to the power 1 plus 2 to the power 0. Next is 256. It can be represented as 2 to the power 8. This 5, that is 4 plus 1, that is 2 square plus 2 to the power 0. Next is 16, that is 2 to the power 4. Again 3. 3 is 2 plus 1, that is this. Now we can consider the two power terms like this. 3 can be represented 2 to the power 1 into 2 to the power 0 into this is 2 to the power 12 plus 15 is 2 cube plus 2 square plus 2 to the power 1 plus 2 to the power 0 into 256 as 2 to the power 8 and so on. We can multiply this 2 to the power 12 with this and this. Now we get 2 to the power 13 plus 2 to the power 12 plus, while multiplying this with all these terms present inside the bracket, we get 2 to the power 11 plus 2 to the power 10 plus 2 to the power 9 plus 2 to the power 8. Similarly, while multiplying this with these two terms present in this bracket, we get 2 to the power 6 plus 2 to the power 4 plus 2 to the power 1 into 2 to the power 0. Right. This 2 to the power 0 means actually a single one. And 2 to the power 1 is 2 itself. Its binary is 1, 0. And 2 to the power 4 is actually 16. We can represent 16 as 1 followed by 4 zeros. 1 with 4 0. 2 can be represented as 1 with a single 0. Next is 2 to the power 6. 1 with 6 0, which is equal to 64. 2 to the power 8 means 1 followed by 8 0. That is 256. Its binary. 2 to the power 9, 512. Its binary is 1 followed by 9 zeros. 2 to the power 10 is 1024. That is 1 followed by 10 zeros. Next is 1 followed by 11 zeros. 1 followed by 12 zeros. 1 followed by 13 zeros. So while adding this, we get this. We don't want to actually add in order to get the number of ones present in the binary representation of this evaluation, because from this it is clear that total how many ones present? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't actually want to add these values. From this it is directly available that total 10 ones are present in the sum value. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So option C is the right answer. Next is the decimal number has 64 digits. The number of bits needed for its equivalent binary representation. A decimal number has 64 digits. Okay, for this, in a base X system, in general, in a base X system, the largest number possible using Y digit is X to the power Y minus 1. In a base X system, the largest number possible using Y digits. We can represent it in general as X to the power Y minus 1. For example, in base 10, the largest number possible using 3 digit is 10 to the power 3 minus 1. That is 1000 minus 1. That is 999. in base 2 with 3 bits, 2 to the power 3 minus 1, that is 8 minus 1 equal to 7. This is the largest number possible in binary system with 3 bits. This is the largest number possible in decimal system with 3 digits. Okay, so its general form is this. In a base x system using y digit, the largest number possible is x to the power y minus 1. So based on this, in a decimal system, that is base 10 system, here using 64 digit. Okay, so we can write as 10 to the power 64 minus 1. This is the largest number possible in decimal with 64 different digits. The number of bits needed for its equivalent binary representation. Number of bits needed for its equivalent binary representation. Binary means base 2. We need to find the number of bits. So while applying or using this formula, here we know that the base is 2 because it is, we are representing binary. Okay, so 2 to the power x. This x actually indicate number of bits used. Okay, 2 to the power x minus 1. So while cancelling this ones, we get 10 to the power 64 equal to 2 to the power x. Now we need to avoid this power term. For that we need to take log to the base 2 in both the sides. Now we get 64 into log 10 to the base 2, which is equal to x into log 2 to the base 2. Log 2 to the base 2 is actually 1, that is x into 1. And here we have 64 into log 10 to the base 2. Right? Log 10 to the base 2 is almost equal to 3.32. Okay, so 64 into 3.32 is equal to x into 1 is x itself. Okay, so x is equal to 212.48, which is almost equal to 230. So option B is the correct option for this question. So next is the hexadecimal equivalent of a binary integer number 11010101. We need to get the hexadecimal equivalent of the given binary number. Okay, so we don't want to convert this into decimal in order to get its hexadecimal. In this pattern, we can directly convert or we can directly generate its hexadecimal equivalent. How? For that, we need to group this binary bits. That is, we can start from our right hand or the LSB position and move towards the MSB position and form different groups with 4 bits. Why this 4 bits? Because in hexadecimal system, the values possible or the symbols using are 0 to 15. For representing different symbols or the numbers from 0 to 15, how many minimum binary bits are required? 4 minimum binary bits are required. Using this 4 binary bits, we can represent all the numbers from 0 to 15 uniquely, like 000, 001 up to 1111. Sorry, 41. 1111 is equivalent to hexadecimal 50. Right? So based on that, we can make different group. Each group contains 4 bits. And we need to start from our right hand and move towards left. So the first group is 1101. Next group is 1010. And here it remains only a single one. Okay, this 1101, which is equivalent to our, now we need to map its hexadecimal representation. 1101 is the hexadecimal equivalent is D. And for 1010, the hexadecimal equivalent is A. And this one, we can add any number of zeros in the left end of a binary. It will not change the actual value. So we can add 3 more 0 to the left end. Now this 1 becomes 0001. This for group actually indicate hexadecimal 1. So 1AD is the hexadecimal equivalent corresponding to this binary pattern. The procedure is starting from the right end, move towards the left and make group of 4 bits. And for each group assign its hexadecimal equivalent. 1101 is equal to hexadecimal D, 1010 is equal to hexadecimal A, and this 0001 is 1. So which option is right? Here option D is the right answer. Okay. Next question is 1217 to the base 8 is equivalent to which of this option? Okay, here three options are with base 16 and option C is with base 10. Okay, so in this case we can first check whether this number is equivalent to any of this base 16. If this number is not matching with any of this base 16, then we can directly conclude here that number is equivalent to this option C. Okay, so we can directly convert this into its hexadecimal form first in order to check whether that number is equal to any of this option A, B, D. Okay, so here we have a simple method for converting this into its hexadecimal form directly. How? This is a base 8 system. In a base 8 system, how many different symbols are possible? 0, 1, 2, 3 up to 7. 8 different symbols. For representing each of these 8 symbols in binary form, for representing uniquely each of these 8 symbols in binary form, minimum how many bits are required? For representing 8 different values, we need 3 bits because 2 to the power 3 is equal to 8. We can generate a different combination. That combination can be used for representing the 8 different symbols of our base 8 system. Right? So here we need 3 minimum bits for representing each of the symbols in base 8 system in its binary form. So now we can generate the binary equivalent of each of these symbols present in the base 8 system. And how many bits are using for representing the binary equivalent? We need to take 3 bits. 7 is represented like using 3 bits. 7 is 111 and this 1 is 001 and this 2 is 010. This 1 is again 001. So this is the binary pattern corresponding to this base 8 system. In a base 8 system, we can directly generate its binary equivalent by considering 3-bit binary equivalent of each of this digit like this. So now using this, we can generate his hexadecimal equivalent. How? In based on our previous example, we know that we can convert a binary pattern into its hexadecimal equivalent by making different groups with 4 bits. We can start from the right end and move towards the left and make different groups of 4 bits like this. The first group contains, we need to start from the right end. 1111 form one group, 0001 that is 1000. The next group 0010 is the next group. Right. So this one is equivalent to hexadecimal 2. This is equivalent to hexadecimal 8. This is equivalent to 15. 15 in hexadecimal represented using F. Okay. So its hexadecimal equivalent is 28F. And also we can add any number of 0 to the left hand which will not change the actual value. So option B is the right answer. So from this it is clear that for converting a base 8 system into its binary equivalent, we don't want to convert into its base 10 then to base 2. We can directly convert this into its binary form. Why? We can assign the 3-bit binary equivalent of each of these symbols present in the base 8 like this. And similarly, for generating the hexadecimal equivalent of a binary pattern, we can make different groups of 4 bits starting from the right hand and proceed towards the left and make different groups of 4 bits like this and assign the hexadecimal equivalent of each of this group properly and generate directly the hexadecimal equivalent of a given binary pattern. Okay, so we can consider some more questions in our next video. Thank you.